sklearn, linear model, ridge. Description. Ridge regression is a linear model that adds a penalty to the sum of the squared coefficients. This penalty helps to prevent overfitting by shrinking the coefficients towards zero. Ridge regression is particularly useful when there is high collinearity among the predictor variables, as it helps to stabilize the model and reduce variance. Inputs. X a 2D array of predictor variables, where each row represents a sample and each column represents a predictor variable. Y a 1D array of target values. Alpha, a float value representing the regularization strength. A higher value of alpha implies a stronger penalty on the coefficients. Fit intercept, a Boolean value indicating whether to fit an intercept term to the model. Normalize, a Boolean value indicating whether to normalize the predictor variables before fitting the model. Copix, a Boolean value indicating whether to copy the input data before fitting the model. Maxiter, an integer value representing the maximum number of iterations to perform during model fitting. Toll, a float value representing the tolerance for the stopping criterion. Solver, a string value representing the solver used for model fitting. Random state, an integer value representing the seed for the random number generator. Outputs. Core a 1D array containing the estimated coefficients for each predictor variable. Intercept, a float value representing the estimated intercept term. Steps. The model first initializes the coefficients and intercept term. The model then iteratively updates the coefficients and intercept term to minimize the loss. Function, which includes a penalty term based on the sum of squared coefficients. The model continues to iterate until it reaches a stopping criterion, such as a maximum number of iterations or a tolerance level. Metrics. Mean squared error MSE, a measure of the average squared difference between the predicted values and the actual values. R squared, a measure of the proportion of variance in the target variable that is explained by K. Predictor variables. Mean absolute error may, a measure of the average absolute difference between the predicted values and the actual values. Visualization plots. Scatter plots of the predicted values vs. the actual values. Residual plots to check for any patterns in the errors. Coefficient plots to visualize the magnitude of the coefficients for each predictor variable. Fine-tune parameters. Alpha, regularization strength. Higher values lead to stronger shrinkage and reduce variance but can increase bias. Use cross-validation to find the best value. Fit intercept, whether to include an intercept term in the model. Typically included unless the data is centered. Normalize, whether to normalize the predictor variables. Can improve performance if the variables have different scales. Uncertainty methods. Confidence intervals for the coefficients can be obtained using bootstrap resampling. Prediction intervals for new data points can be obtained using bootstrap resampling or Bayesian methods. Challenges and fixes. Challenge 1, overfitting. Sample use case that resulted in challenge 1 using a high number of features with a small amount of data can lead to overfitting. Fixes to challenge 1 use a regularization technique like ridge regression to shrink K coefficients towards 0 and reduce overfitting. Challenge 2, multicollinearity. Sample use case that resulted in challenge 2 when multiple predictor variables are highly correlated. This can lead to unstable estimates of the coefficients. Fixes to challenge 2 use ridge regression, which adds a penalty to the sum of squared coefficients and helps to stabilize the estimates. Challenge 3, scaled features. Sample use case that resulted in challenge 3 if the predictor variables are not scaled. The model can be sensitive to the scales of the variables. Fixes to challenge 3 normalize the predictor variables before fitting the model.